First of all, Mahout, why Mahout is a powerful choice for the classification. Before we start the classification itself, whenever say because in the classification also we will give the data to the system, and then from that data only system will run and it will continue. So that thing I will explain later, but just from the starting itself that why Mahout is there. So if file size number of examples like which we are giving to the system to learn and all, it's less than around this 1 lakh. So what will happen that like non-Mahout system will also work very well, and Mahout actually works slow in those sort of scenarios if data is low. But if it is like 1 million to 10 million range, then Mahout is really excellent. And if your data size is increasing greater than 10 million, then Mahout is really achieve the things which other system cannot achieve. Like it's really excel from the others. And if you will see the performance graph and all, so its performance increase exponentially if the data size is greater than 10 million. So that's how that's why Mahout is a popular choice of the classification. And in the classification side, there are certain algorithms like as we saw in the clustering also. So for the classification also there are certain set of algorithms. So in that one, Mahout, not all in the classification field, but certain algorithms are implemented in the Mahout, which we can directly use. So if you will see this classification is actually a 3-stage workflow. One is like training the model, and then evaluate and tune the model, and then once your model is ready, you are pretty much satisfied with the performance metrics and all, then you can use that model in the production. So that's what actually classification in these 3 steps are there. So basically classification is a process of using specific information to choose a single selection from a short list of predefined potential response. Classification and clustering. Like clustering is an unsupervised learning in the machine learning field, if we will say by the definition, and classification is supervised one. So as we discussed earlier also, in the classification problems, we know the input set, we know the output set also. Like if I'm giving the data to the system, I know that okay, for this particular input, this is my output. And then we are making a system to learn from the previous data from input and output to predict for the next set of data to predict the output. While in the clustering, what we were doing, we don't know the output and all, we just have the data. Based on some certain properties, we are clustering it around that okay, these data is looking similar, so put it in one cluster, other data is looking similar, put in another cluster, and then some new data is coming to the system, and based on that distance calculation, we are putting in the different cluster. But here what we are doing, we know the input and output already. So let's say for an example, if we will go in a particular area, if we wanted to know what is the house price or land price is going on. So we will have some historical data that okay, per square feet in this particular area is going in this price range. So we are having a lot of data, and then we will create a model so that if I will put a square feet area into the system, it will give me the output that okay, this price range you should get, that in this price range you will get this particular property. So that's how classification works. And if you will see this classification problem in Mahout, it requires resources that increase no faster than the number of training or test examples, and in most cases it computes resource requirement in a parallel way. So as I told you earlier also, this classification is a process of using information to choose a single selection from a short list of predefined potential responses. So already if we will collect the data, we know the input and output, then only we will go ahead with that. So, and this classification problem are actually, if you know this, they are main core of the predictive analysis sort of problem. So based on the previous data, we will learn something and then we can predict for the future. So and the goal of predictive analytics is to build to build automated system that can make decision to decision similar like the human judgment. So if you will see the examples of this particular thing, so in the iTunes, so it classifies your songs based on the user playlist choice or based on the artist or something like that. So this is a particular example of the classification. So based on your previous thing, we know that okay, for this particular song belongs to this particular men, so they can define your playlist. Main example of the classification, classic example, is the spam detection, and this is where actually Yahoo spam detection, they have started to set up the Hadoop also they use for this spam detection things and all, because data is huge here. So for the incoming mails based on the previous email histories, which they can find out from the who is sending that mail, what is the subject line of that mail, what is the body in that mail. Based on these criteria, system can identify that whether to put this email as a spam or as a regular email. So that's how the system will classify that this particular incoming email, it's a spam or it's a simple email. And if you will see now, recently Google has also started this sort of thing. If you will see, our email box has been changed a lot. Like we are having this primary, social, promotional, and those sort of classification. So based on certain things, like if invites are coming from the Google Plus side, then put in the social or some webinar invite or something like that. And primary is where your regular emails are coming, and promotional is like some sort of ad from the Amazon or from let's say for example from Edureka side and all. So those will go on the promotional side, and based on these particular classification only, you can find out that okay, if it is not falling into this category, it is a part of the spam and all. So that's how they will calculate, and it will go on. So advantage and disadvantages will so in advantages are for the classification that system is trained. Classification is done automatically. So once you are having the data, you will put a learning algorithm in place. Algorithm will learn based on the data. Then some of the data you will use to test that model, and once your model is ready, you are ready. So there is a very less thing from your side, apart from you will put the algorithms and all, and it is like consistent in the classification. Once your model will there are certain performance metrics which we will see today. So if that model is up to those performance metrics, it will always be consistent in 95% of the cases. If your data is not changing that much or certain assumptions which you didn't take care in advance, so it will give you consistent performance. And other thing is like human resources are not needed to make rules. So system will generate, the learning algorithm will generate the rules based on the data only. So you are not specifying any parameters or any other things there, so that system will not learn. And disadvantage side, if you will go, so not always obvious why it classified a document in a certain way, or not obvious how to keep it from doing the same type of classification in the future. Okay, I would say it is yeah, if you are not doing proper set of predictor analysis and all, then yeah, this could be advantage if you will not define what are the parameters which can affect my output. Like let's say for the property price also, if I will say, there could be like location in a particular city also which can affect your prices. So if you will not take care for your feature metrics properly, then it could be a disadvantage for you. And human resource must be used to manually classify document for training set. Obviously, once you will start, once in the classification problems you will start, you have the data. So you are the only one who will define that okay, this much of data I will use for training, this much of data I will use for the testing and all. So yeah, that is little bit of the disadvantage side. But apart from that, classification, once your model is ready, based on all the variables which can affect, if you are including all the variables into the system, then it is more robust. So classification, if you will see this classification algorithm, it learns by example, and they actually can substitute the human judgment once your model is ready. So that is the intention, that instead of you are judging, the system should give you the real output. And application side, if you will see this prediction or detection of the credit card fraud, it's a very good example of the classification. So based on the user's previous history of how it uses the credit card payment details and how it is his purchase habits, based on that, system can predict that okay, particular transaction was a fraud or it was not a fraud or a genuine one. So that's way it can predict. And it is also in the industry wise, if you will see, the classification is very much useful in the insurance and the telecommunication industry. So insurance, like you can create based on the user previous history and buying habit or in any other thing, you can predict that okay, whether the this customer will continue the next year also for the insurance, and based on the telecommunication also, like for a particular service, like in India it's like Airtel and Vodafone. So it will continue or not. So in those particular industries, this classification is heavily used. And how it works means, if you will see in this applications also, there are only two main phase. Like you will create a model reduced by a learning algorithm. There will be a learning algorithm which will produce a model, and you will use that model to assign new data to the categories. So okay, we'll just move to the next slide. Then you'll see how it works. So you are having the training examples with reference decision, and there are we will discuss about this predictors and target variables. So target variables are like your outputs, and predictors are which can affect your output. So based on these two, you will define these two parameters, and your training algorithm will be in place. Your algorithm will learn based on these parameters from the system, and then it will create a model. So this training algorithm, sometimes it is called a this hypothesis also, that based on the previous year data you are creating a hypothesis, and then based on that hypothesis you are creating a model. And once your model is ready, after a certain performance metrics you will do on that, like area under curve and your confusion metrics, your entropy metrics and all. These are the primary performance metrics you will do on that model, and once it is done, you are sure that okay, your model is predicting pretty much okay, then you will put in the production, and then new examples will come which are already unknown to the system, and it will give you the target results. And in the real classification problems, this model will be like reinvented again and again. So once your new examples are coming, model is generating outputs, then again this same set of outputs will again load to the system. Again training algorithm will regenerate the model, and this model will again come as a production model. So it's like a never-ending process, and you should actually take care of your model updation on a regular basis. That okay, your model is updating or not. So if you will see this in this particular diagram also, this dotted one, which is red dotted, it's like a main component, your training algorithm, your model, and your model copy to the real production system. So I would say this arrow which is coming from model to model, it's a two-way. So again and again this emulated decisions will go back to the training examples with reference decision, and then training algorithm will again generate a model, and it will give you the model again. So this selection of training data algorithm through which system will learn the variable used as an input and are key for this particular choice. So this particular training data and variables which we are choosing for the predicators and all. So predicators we will just see now, predictors versus target variable. So target variables are the variables whose are to be modeled and predicted by other variables. In short, in summary, it is going to be your output, okay, the target variables. These variables which will predict by the system. And if you will see the predicators, these are the variables whose values will be used to predict the value of the target variable. So if you will remember your your chemistry classes and all, so there was something called catalyst which can change the which will generate the faster outputs for the equation and all. So same goes with the predictors also. Choosing your predictors rightly can affect your outputs. So predictor from your data set you will find out what is going to be your predictors, and these will help to predict the target value. And if you will see your predictors are of 4 types into the classification side. So based on these predictors only this target variable will be generated, and how the types of the predictors, how you will define those predictors into the system so that Mahout can understand. So just for a hint, again this vectorization process and all those things are there also. Here also, like in the clustering also there was a certain form of input only which Mahout will take care, like vectorization. Same goes here also. Little bit, I would say little bit more addition for that, but it is still same. So, okay, predictors versus target variable. If you will see again, in production, the target variable is the value being sought for each new example. In training, target variable is known for the historical data. So, as again and again I am saying, I know the input and now I know the output also when I am starting my training algorithm for the model. So, their target variables is the from the historical data I know the target variable. In classification, the predictors variable are the clues given to the model, so it can decide what target variable to assign to each example. And in the predictor variables, it's used for classification, also known as input variable or predictors. So that is all about. So just keep this thing in mind. When I'm training the system, I know the target variable already in advance. That's how I'm training. Once I'm in the training, I will use the predictors to affect my output, and once all the things are ready, I will generate a model and I will use that in the system. So these predictor variables are of it's, as I was telling you, of 4 types: continuous, categorical, word-like, and text-like. So now what this means in this one: continuous means like your floating point values from the data. Anything means anyway these predictors and other things are coming from the data only, or historical data. So continuous means it is like a floating point value. So as we were saying, I was giving an example of the balls. So weight, which is a floating point I can decide, or let's say in some certain conditions price, or other numeric things which can affect the output, is as a part of the continuous predictor variables. If you will see this categorical one, it's like a generally Boolean value. Boolean value generally treated as a categorical one. So it is like a pre-specified value, and it is like simply like true or false or yes and no sort of thing. If it is there, let's say for a property, if I'm saying this, if color of this particular ball is red or green, so like this yes or no sort of answer, so that will fall as a categorical one. Word like here is like open-ended set of possible values. Your simple text values and all those things will come as a word like. Text like is a advanced form of word like only, combination of word like features. And in the text like, it will like your email addresses, your URLs in the data, those will fall as a text like things, as a text like predictor variables. So again, just to remove certain confusion, like I told you, continuous will have the numeric values, right? So it can also happen like your zip codes. For any state we are having the zip codes and all. So where you will put that zip code? So if you will see, generally idea would be like, okay, numeric values continuous, so I will put in the continuous. No, zip code will not be a part of the continuous. Zip code or any values where after doing average or square root, or if it is not giving you any useful information for that, you cannot put in the continuous one. You will put at a category one, those things. So classic example is like your zip codes, where from based on the zip code you can find out certain things yours in the classification problems and all. So those you cannot define as a part of the continuous one. It will come under the categorical one. And generally things which are associated with the unit of measurement, they would be part of the continuous variable, like your weight or your price things and all, which are certain unit of measurement is there, they will part of a continuous one. Otherwise they will be a part of the categorical one. And if finite group of pre-specified values are there, generally categorical one we will put. If that finite group is not there, we will put in a word like one. So you will get more clarity once we will move into this particular part. So let's say this one. So this is how it is defined, like continuous floating point values. The value, the type of value might be price, weight, time, or anything else which is a numeric thing. But as I told you, this zip codes are also numeric. It will not part of the continuous. So you can just associate something unit of measurement should be there. Categorical one, set of pre-specified values. Typically the set of category values is relatively small, and it is like generally a Boolean sort of thing. Same goes with your, it's vendor IDs also, vendor IDs or user IDs, because those are actually numbers, but if you will see, you cannot do anything with that number, or they will not define you any specific thing. So obviously those things also will be a part of category one. Word like is like a category only, but it's an open-ended set of possible values, and text is a sequence of one. So means if combine words like this email addresses and URLs are also text like. So these are the type of the predictor variables. So if you will see when we are taking the example of the email spam, so this predictor means an email is a spam or not. So if you will see the first column, these are the things we will define for the in the total data set. We will take these things, and certain things we will take as a part of the predictors to define an email is a spam or not. So if you will see this from address, like who is sending the email and all, it's like a word like thing, because it's a means it's simply a word, means from who is sending this particular email. Address book means in address book this address is existing in your address book or not, just a Boolean sort of thing. So obviously categorical. Non-spam words, because they are a bunch of words or a combination of words can occur, so it's like a text like thing. Spam words, for the spam also you will define certain words in the spam category. So those words also text like. Unknown words we will say the continuous, and message length also we will put in the continuous part. Okay. This feature extraction. Feature extraction is nothing but from the data you wanted to extract certain features. Like whenever I'm saying data, you don't know anything about that data. So obviously you will have to go through that data once before putting it to some system and all, and then you will find out certain things as a target, means what is going to be my target value, what is going to be my predictors, what is going to be my input and all. So these things are called the feature extraction for that particular thing. And once you will, from the raw data, we will do certain sort of pre-processing, and then take training example with reference decision will be the output for that, and that thing we will use for the training algorithm. So directly raw data we will not use for the training algorithm. So if you will see, this raw data must be collected and pre-processed before using in the classification example. And pre-processing raw data means you will rearrange data into the records, and you will find out this field like continuous, categorical, word like, test like, what is there. And for this pre-processing there is no hard and fast rules. It is certainly based on the experience and your intelligence case, that okay, how I will find out this predictors and how I will define internally these predictors in which category. So this is based on your experience and intelligent guess sometimes. And then once it is there, done your pre-processing, you will convert that data to the vectors. So as I told you in the vectors thing, in the clustering also we used. So here also we will convert into the vectors. And there for the vector encoders in the Mahout there are certain analyzer also required. So generally we use Lucene analyzer, which will actually tokenize the your input data. Like it will provide you filters also, like if you wanted to remove the spaces and punctuation marks and all. So those things are also will come into picture. So that's this is the phase which I was saying. In the raw data you will do certain things like joining, combining, transforming, and then you will put your training examples with target value. You will do certain sort of parsing so that Mahout system can understand what sort of data you are putting. You will create a tokens and you will do encoding of these tokens using the vectorization process, and these tokens you will put in the training algorithm. So vectors are the format that the classification algorithm requires as an input. Same goes with the clustering also. There also we were creating the vectors. Here also we are creating the vectors for the classification algorithm. So here it is a two-step process, like tokenization and vectorization. So in the tokenization process we will use certain analyzers like third party also we can use, but generally the Lucene one will do the job for us. So if you will see this here, we will try to build a classification model that will determine whether a user will buy a particular product if they are offered it. Okay. So here if you will use this type of particular problems, there would be a different tables will be created in the system. And why this example is here is like processing of your raw data. So if you will you cannot directly use these tables into the classification examples and all. You will have to write a simple query which will take the product ID, username and offers, other things, and you will write a SQL query. This will give you your output, and then that SQL query you will use as an input so that it can collect the data from all the tables. So that's why this pre-processing is always required in terms of the classification things. And okay, feature extraction is nothing, as we were discussed earlier also. It is like from the data you just wanted to find out these four types: continuous, categorical, word-like or text-like. And raw data you will use for the vectors. For the classifying data you will tokenize and vectorize. Those two processes you will do, tokenize and vectorize. It's vectorization process. Okay. So vector, obviously it's a data type. We saw this vectorization in the clustering side also, but here it looks a little complex, but actually it is same only. So it stores the floating point numbers indexed by the integers. Okay, it saves the floating point numbers. So we will have to convert our data also into these numbers, and then we will save into the vectorization. So if you will see this representing data as a vector, because Mahout will only take the vector, there are approaches, three approaches are there. One is use one vector shell per word, category or continuous values. These word, category and continuous values is nothing but your types of the predicators. And second approach is represent vector implicitly as backs of words. And third approach is using feature hashing. So we will see what these three approaches are and how we can do theoretically, and then I will run an example also so that you can find out that okay, how to create the vector out of your data. Okay, so this one shell per word or category or continuous value, so it is a way to encode your your classifiable data as a vector. So what it does, it will take two passes. So the training data, whatever data you will do, it will make two passes. One to determine necessary size of the vector, that okay, what would be the vector size if I will take all these values into account, and then it will create a internally dictionary to remember which all the features should go into the vector, and then it will create your particular vector of this shell per word with the two passes. So obviously you don't need to take account of all these things because we have already APIs for that also to convert this data as a particular this approach. So what it does, it's a simple representation of encoding, training, and text example. And other thing is like vectors as a bag of words. What it will carry around the feature numbers, feature names, or names plus categories, or words or text value instead of carrying around the vector object. And then in Mahout, this particular second sort of vector will be used in the naive Bayes algorithm, not in the SGD. Feature hashing is the one which SGD use. What it does, it will calculate a hashing for that particular predictor value, and then based on that hashing, it will put those words or text-like field into the vector. And this feature hashing thing for the encoding, we have two approaches actually for this. One is adaptive word value encoder, and other one is the static word value encoder. So adaptive word value encoder, what it does, it will build a dictionary on the fly and estimate the word frequency. So if you remember the word frequency which we did in the clustering side also, so same thing, but it will give the longer way to the rare words. So for this it is a adaptive word value encoder. Second is static word value encoder. It does it will supply dictionary or given equal weights to all the words into the dictionary. So this is the one means like three different categories, and the encoders are like feature encoders, which are for categorial and word like we are having this adaptive word value encoder and static word value encoder. For text type also we can use the same one. And it's nothing. It's defining the same thing as I told you. The feature hashing SGD based classifier avoids the need to predetermine vector size by simply picking a reasonable size and shoehorning the training data into the vectors of that size. This approach is known as the feature hashing. So instead of running the two passes, it will just take one. It will not make any size of the vector, and on the fly itself it will create. So this one SGD is this 20 news group data we will use for the naive Bayes and random forest things, not for the SGD. SGD one we will use the same stock market option which I told you. So what we will do, we will download a stock market data from the Yahoo Financial site, and we will manipulate that data in a way so that we can use in the Mahout online logistic regression one, and then we will try to make a model which can predict us whether on a particular day we should sell a particular stock or we should buy a stock. So that thing we will see with the SGD. And coming means before we will go to the naive Bayes and 20 news group data. So this 20 news group data, if you will see, it is having like Reuters data only, but the difference it is having one dictionary per news group. It is also having the news group, and it is defined those news groups into the 20 different articles. And our aim is to make a model so that a news article can be classified in one of the 20 groups. So if you will see, this problem is not like binary one. It is having the 20 different approaches, 20 different outputs, I would say. So I will show you that 20 news group data once we will do this naive Bayes thing. So for that 20 news group data also, we will have to first do some vectorization and tokenization for that, and then only we will use that particular data. So let me just show you one more example where the steps are defined. I have commented the steps that okay, what are the steps you will have to do before using one particular data set. Naive Bayes classification. So first of all, to understand this particular algorithm, we will have to take care of what is basically this algorithm is and on what are the things it is based upon. So generally this naive Bayes theorem, is actually based on the Bayes theorem, which is related to the probability distribution theorem, and it is based on the conditional probability. So we will take one example of the Bayes theorem today, and then we will see how this naive Bayes theorem will use that Bayes theorem to classify certain items. So starting with the conditional probability, as I told you, so conditional probability is, finding out a probability of one particular thing given that other thing already happened. So let me switch to this one. So how we denote this, that let's say I wanted to know a probability of A when I am saying that P has already occurred. So in this way we will denote this. So this symbol shows that probability of A and B has already occurred. So now, first of all, I will just give a definition of the Bayes theorem. Then we will see with an example that how it works. So what in the simple English term, what this Bayes theorem says, just let me write down this thing and then I will explain to you. It is like posterior probability is equal to prior probability of an event and then multiply by likelihood of that event, and the whole thing is divided by evidence. Okay, this is in the simple English term, that how this Bayes theorem define the things. But if I will go to the mathematically one, as I have already told you this conditional probability concept, how we will define this. So if let's say I wanted to see a probability of A given B, so the formula says that it would be probability of B given A multiply probability of A, which is called a prior probability, and divide by probability of B. In this way, this is the mathematical formula for the Bayes theorem. So now to understand this, we will take an example that okay how it works. So as I told you, this is based on the conditional probability, and it is little slightly different from the our original probability problems. It is like, let's say one guy is saying that I had a conversation while he was on a journey, he was having a very nice conversation with a person. So if we are just hearing this line, so what is the probability that he is having a conversation with a man or a woman? Obviously we don't know anything of the event, so we will just say that this probability whether he had a conversation with the man or woman is 0.5, right? So the probability would be like 0.5 only. We don't know anything about the earlier conditions. Now let's say he is saying that he had a conversation with a person who was having a long hair. So now other condition are also given in this problem. So now we will have to calculate what was the probability that he had a conversation with a woman, given that that person was having a long hair. So if I would like to write this in mathematical form, it would be like this. So what is the probability that he had a conversation with a woman given that he was having a long hairs, right? So mathematical in term, if you will see how we will define this. So before that, before writing this, there are certain other conditions also. So let's say we have given in our problem that 75% of the women would be having long hair and 15% of the men will have the long hairs. Now how this formula will work in this given condition. So we are given that if a person is having long hair, let me write it this way, long hair, and if it is a woman, then probability is equal to 75%, or I would say 0.75, right? Same goes with the other condition also, that we know that if he is having a long hair, then what is the probability, what if it is having, he is a man and having the long hairs, so what is the probability for this? Is 0.5. So these two conditions we know already. Now let us calculate mathematically, and we know one more thing before doing any other thing, that whether it would be a man or woman, this probability would be 0.5. So let me define this thing also. So using the Bayes theorem, how we will define this whole formula, I will come back to here. It would be, as we saw this probability of A when B was given, so we will define this in this scenario. Means we have given that person was having long hair, and he's a woman, multiply by, because we wanted to know that what is the probability that a person was a woman given that he was having the long hairs. Okay, so and total thing divided by evidence, which is probability given probability of long hair when it is a woman multiplied by probability of was a woman plus and probability of the long hair when it is a man. So multiply by probability of man. So using this formula, and we know all the and the same goes with the probability of men also, that it is without knowing anything we can say 0.5. Right? So now we have all the values in hand with us. So we will directly calculate that what was the probability that the person to whom he was having the conversation is a woman, given that he was having a long hair. So that's how this Bayes theorem works. And in this Bayes theorem, actually idea is to come up to a conclusion. We were having a probability of evidence based on the known outcome, and we wanted to know probability of an outcome based on the known evidence. So in simple term, it is like we wanted to know the probability of a evidence when we know the probability of known output. So when I will define this formula, so based on this formula only we will head towards the naive Bayes classifier. So we know this thing, and we wanted to achieve mathematically probability of an outcome given that we know the known evidence. So this is the intention behind the Bayes rule. We will do this thing. We know the probability of evidence given that a known output, and we wanted to know the target value given the known evidence. So how this naive Bayes work, because naive Bayes will work on the multiple evidence. We would be having a data set in which we were having the multiple evidence. So for that case, the formula will change like this. We wanted to know the probability of an outcome given that multiple evidence. We are giving the multiple evidence, and then this formula will change like probability of evidence 1 given the outcome multiply probability of evidence 2 given the outcome, and then it will go on till a number of times, then multiply by the probability of outcome, and the whole thing will be divided by probability of evidence. So it is something like let's say I am saying evidence 1 given that outcome multiply probability of evidence 2 and given that the outcome, and it will go on till the n number of evidence, whatever number of evidence we are having, multiply by probability of an outcome, which is called a prior probability, and full thing is divided by the probability of evidence. Okay, so in this is the formula of the naive Bayes thing. So what generally do for this thing, we run this formula for all the possible outcomes, what could be the outcomes, and then for each outcome we will define a class and we will assign a label, because we know already that in what label this class would be, and then we will calculate the probability of all the such classes, and whatever is the maximum probability we will assign that particular item to that class only, that okay, now it is for that class. So okay, coming from this theoretical thing, let's take an example that how this in the real situation this naive Bayes work. So for that thing you will have to consider this particular table. Okay, we have given a table in which we were having three type of fruits. One is banana, other one is orange, and one other fruit also is there. We don't know anything about that other fruit, and we were giving some characteristics also of those fruits. So let me define those characteristics here. So we were giving that one characteristic is size. Okay, so in this size one we have given that whether the fruit is long or not, just simple one, long or not. Second thing is we have given a taste, whether a fruit is sweet or not. And then third thing is whether about the color of that characteristics, so whether color is yellow or not. Just three characteristics we know in advance before starting our naive Bayes classifier, and we were given this all the details also. We were having total 1000 fruits, which we can see here, and in this 1001 we have 500 bananas, 300 oranges, and 200 other fruits given, and then other distribution also we have given with the characteristics for the size, that long fruits, not and which are not long, sweet and not sweet, yellow and not yellow. So all the details were given to us. Now the question is, we were asked to classify a fruit. We don't know anything about that fruit, and we were given that that fruit is a long and it is sweet and yellow in color. So what would that fruit be, whether it is a banana, it is an orange, or if it is an other type of fruit. So based on this Bayes theorem, this our naive Bayes classifier will find out what it is. Okay, then how we will find out this thing using that probability theorem. So first of all, we know our prior probabilities. We will have to find out that thing. So internally this naive Bayes algorithm will find out that okay, what are the prior probabilities, what is the likelihood, what is the probability of evidence, and all those things. So for this example we will calculate ourselves that okay, what are these things. Okay, so what we know about in advance, we know if a fruit is banana, what is the probability that a fruit is banana. So we can find out this thing immediately that okay, total number of fruits we were having 1000 and we are having the 500 bananas. So simply I can say 500 divided by 1000, so my probability for this is 0.5. Now for the, if let's say for the orange, that is also a part of the prior probability, that also simply I can find out 300 fruits are orange and total is 1000. So again for this one I have probability 0.3. Now for the probability of the other fruit, so that also from the example only we can find out. We have all the data for this, and it is like 200 divided by 1000, so we are having 0.2. Okay, fine. So these things we are having already in advance. Now probability of evidence also, because if you will see, the idea was Bayes theorem was having this thing, and then if you will see naive Bayes was having this formula. So we will get all the things whatever we were having in hand, and we will try to come up in a mathematical form to find out that based on the characteristics how we will classify that particular fruit. So probability of the evidence. So what are the things we know? We know for the evidences are like our characteristics. If fruit is long, what is the probability of that one? So if you will see long fruits, we are having, we will go with this first column 500. So 500 divided by total 1000. So we know this probability is 0.5. And now the probability of sweet fruits. So the in the given data set. So if we will see in this sweet fruit, let me just pull it up. So we have 650 sweet fruits. So obviously 1000 fruit total. So 0.65 is the probability for that. And then one more characteristics we are taking care, that yellow, or I would say color. And what is the probability that a fruit is yellow? For that characteristic, we know 800 fruits are yellow out of 1000. So it's 0.8. Simply identify that also. 0.8. Okay. Now we have all these things, but now we will have to find out the probability of the likelihood also. That what is the probability of likelihood? Now what is the likelihood? So let me define here only. Probability of likelihood. In this one, what we will define, we'll define like this. Probability of a long fruit given that it is a banana. So there would be many like this likelihoods. We will have to calculate all, but we will see some of the examples for this one. So if I know that okay, fruit, given that I am having a banana, so what is the probability that it is long, something like that we will say. So what will be the probability for this? So if you will see total, go here, total long fruits which are banana, it's like this number 400. So 400 out of total banana is 500. So 400 out of 500. So my probability is 0.8 for that. Okay. Same way we will calculate other probabilities also, like probability of long if given as orange. This one also I will mention because we use this effect of formula. And it is a orange. So if you will see this probability, if you will see the table here, so orange in this category, the long and orange is 0. So 0 divided by whatever total number, it will become the 0 only. So we have this probability as 0. And then we have one more others likelihood also. We will take care like probability of a fruit if it is yellow, given that fruit is a other fruit. So we know that fruit is another fruit, and if it is yellow, so what would be the probability of that? So I can find out here. It is like other fruits, total other fruits are 200, and if it is a yellow 50, so 50 divided by 200. So what that would be the probability. Let me define this also. Probability of yellow color fruit given that it's an other fruit. So we saw it's 50 divided by 200. So how much is it? 25. So in this way we can find out other likelihood probabilities also. So now we have given already the problem set was that we are having a fruit which we don't know in which category it is, and it was long, sweet and yellow. So classify this particular fruit. So we are having, actually if you will see, we are having 3 outcomes based on this particular formula. Now how 3 outcomes? Because we are having the 3 fruits. In these 3 we will classify this. So what we will do, we will see that what is the probability that a fruit is banana given that fruit is long, sweet and yellow. So define this thing here. So what we wanted to calculate, we are having 3 outcomes. One is what is the probability that this given fruit, which is unknown to us, it's a banana, given that it is long, it is sweet, and it is yellow. Then other outcome would be, I will write down the formulas for this. Second outcome is this fruit is an orange, given that same thing, long, sweet, and yellow. And the third outcome would be, what is the probability that this fruit will be of the other category given the same thing, in the same condition. So now how we will find out? So we will calculate individual probability of whether it is a banana, orange, or other fruit, and whatever probability would be higher, that category we will assign to this new fruit. That's how this naive bias will work. So formula for this, let's say we are saying that it's a banana, what would be the formula? So if you will see multiple, this is a sort of multiple evidence sort of thing. So we have evidence 1 given the outcome. So we know we are considering this is a banana, so and we know it is long given that it is a banana. Okay, multiply by probability of other, if you will see this formula, other evidence, it's a sweet and we know it's a banana, and then we know the third evidence also, that it's a yellow, okay, and given it is a banana. And if you will see that total, we will multiply with the outcome we are considering it's a banana, and the whole thing is divided by the probability of evidence, means probability of long multiply probability of sweet multiply by probability of yellow. So I will just write here the whole thing, probability of long, and if you will see, we know all these things now based on our data set. We know all these probabilities already in advance, so it's just a matter of calculation. So, and probability of yellow. So if you will see the same formula, I am considering that unknown fruit is a banana given these characteristics. So how I will find out this thing? It's a long given that it's a banana, sweet given that it's a banana, yellow given that it's a banana, multiply by probability of having this fruit as a banana, divide by total number of evidence, which is long, sweet, and yellow. So this one formula is for calculating that this is a, what would be the probability that this unknown is a banana. Same way we can, now you can find out the formula of this orange also. So what we will have, probability of long given that it's an orange, probability of sweet given that it's an orange, and yellow it's an orange, like this. And same goes with the other fruit also, these three formula. So if you will see, if you will put all these mathematical term into this one, so we have calculated below what is the probability, it's a long and banana, it's 0.8, multiply by it's a sweet and it's a banana, that also we can find out, sweet and banana. So let's say in the table we are having, where it is, okay, it's a sweet and it's a banana. So total sweet is sweets and banana 350 out of 500. So it would be around 0.7. So like this. So whatever given there, we know everything, that it's a yellow and it's a banana. For this one, it will come out from this table. 0.9 and multiply by it's a banana 0.5 and divide by, so this below calculation we can still make as a probability of evidence, no issue in that. And if you will find out this calculation, it is coming out as let me write it here, coming out as 0.252 divide by probability of evidence. I'm not calculating that because that term is similar in all my outcomes. So it's okay not to calculate that also. So probability of orange, if you will find out this probability of, we have already covered probability of long, given it is an orange, it's 0. So obviously this particular term will come here in this formula, probability of long, and it's an orange. So obviously the whole term will be as a 0. So probability of that fruit is becoming an orange is directly is a 0. And then so the main contender would be this other fruit and the banana. So for the other fruit also we will calculate the probability, and then we can find out in the same way that long and it is other fruit, and sweet and other fruit. In this way you will calculate, you will find out that this probability, I have actually already calculated this probability, it will come out as something like 0.1875 divided by probability of evidence. Total evidence means probability of long into probability of sweet into probability of yellow. So obviously if you will see, now we have all the three outcomes probability. For banana it is 0.252 divided by probability of evidence. For orange it is 0, and if we are thinking it's another fruit, probability is this one, 0.1875. So totally if you will see this fruit, unknown fruit, which we were giving the characteristic, it was classified as a banana. So that's how your whole this naive Bayes algorithm works, based on the Bayes theorem, probability theorem. And it is like it is classifying based on the probabilities. It will calculate a probability that okay, what could be the probability that this particular outcome is a part of given all the classification classes, and whoever is having the higher probability, it will assign to that class, that particular class. Random forest algorithm work, it will create the different decision trees, and it will classify based on different decision trees, different classes it will calculate. Like if you will compare with the naive Bayes, it is not, you cannot directly one-to-one compare, but just assume in their one we were calculating the different probabilities based on the outcomes, and whatever is the highest probability we were taking that. Here we will generate the mod of the classes and output by individual tree, and then that would be our output class, that okay, whichever is having the higher one, assign it to that one. So here you can see in the slide also. And one more thing, for the naive Bayes algorithm also, it is actually good if your data set is more than 10 million, and so parallel calculation can happen. So in that form, naive Bayes is really exceed from other algorithms. So in the random forest, problem is, if you will see the memory consumption. So for each node in the cluster, it will consume the memory in a proportion to the square root of the number of training examples it is using. So that's why memory consumption is little high in the random forest one, and that's why it is saying it's not quite as good as naive Bayes, where memory requirements are proportional to the number of unique words seen, and thus are approximate to the log of those number of training examples. So here it is directly proportional to the number of training examples in the random. One more algorithm was there, like support vector machine, but I would say it was there. Now it has been removed from the new APIs in the Mahout. But just for the definition wise, what was the support vector machine was? It was non-probabilistic binary linear classification, that SVM. So for when you are having this, two category in the target value, then it was very good. But recently these classes are not there now in the Mahout side. So that SVM model, that is a representation of the, you can just for the definition sake I am telling you, it's a representation of all the examples as a point in space you can consider. Like you have the coordinate geometry sort of thing, so all the examples you can see as a marked in a space, and then you can map those examples to the separate category, and when you will define those points in a separate category, so there should be a gap also between those categories, so that we can say that okay, this example is fall in this one and other examples fall in this one, and when the new example will come in that space, so it will be based on the calculation, it will be predicted that in which category it will fall on. So in that particular gap, that new point, if it is close to the one particular gap, it will assign to that one. If that distance is close to the other one, it will assign to the other one. So that's how the support vector machine works. So now actually if you will see this, if you will try to find out in the Mahout algorithm side, it is not there. So we cannot do much in that area as of now. So going back to the slide again. Okay, now it comes as a part of your evaluating classifiers and your tuning classifiers and what are the other things you can do with the different metrics. So if you will see this when we are making our classifiers in a Mahout or in any using any APIs and all, so that evaluation of those are really very much required. So I will give an example why that is required and what are the problems can occur if you are not doing that properly. But before that, the metrics which Mahout provides are like different set of metrics Mahout provides to measure the performance of the classifier, like percent correct, confusion matrix, area under curve, and log likelihood. So just let me just go into the system and we will see if you will see the API which Mahout provides. So for the AUC, if you will see that there is already a class there in the whole library, so you can find out that okay, what is area under curve. So a little bit of definition in the API, and it will give you all the mathematical formulas also, that how it is calculating, how when we are providing our algorithm, that hyphen AUC metrics we are doing for the model, so how it is working and all. So you can find out this here, and there is one more like confusion matrix also there. So if you will see confusion matrix, it is already defined there. So there also in the APIs you can go ahead and you can find out. The confusion matrix, as I defined yesterday also, it was same thing. The actual values will be in the rows in the matrix and the predictive values will be in the column. And then we will try to create a metric, I would say a 4-dimensional thing, not 4-dimensional, 4-part thing for the true positive and true negative and false positive and false negative, and then we will try to find out whether our model is performing well or not. So these are the different matrices which are already defined there, and we saw the AUC also, that area under the curve model that produces a continuous score for binary target variable. So now the thing is, as I was telling you, this evaluation, why it is really important. So if you remember, let's say let's assume we are having two particular categories where we wanted to classify our items. So let's say A and B, we are having two categories, A and B, and we are having certain items called A1, A2, A3 and B1, B2, B3, and we wanted to classify that thing. And in that one, let's say your system is classifying properly, and then we will evaluate the metrics and all. So what can happen there, you can find out certain false positive and false negative also, correct? So in the false positive, if you will see, false positive is the thing, as we discussed yesterday also, where a particular item which is falsely classified as in a different category. So in our example, let's say we are having A and B, two categories, and we are having 6 items, A1, A2, A3 and B1, B2, B3, and we classify B2 in A. So this would be a false positive, because that B2 is supposed to be in the part of the B, but we classified in the A. So if you will see in the real scenario, this particular scenario where false positive are coming, the cost of this false positive is actually less than the cost of the false negative. So in the false negative means the criteria was like A1 was supposed to be a part of A, but we put in the part of B. So let's say a real-time scenario example. Let's say we try to find out a cancer that doesn't exist, and that cancer doesn't exist, and we just wanted to try out whether in which category our classifier provided it. So just see this example, that finding a cancer that does not exist has an expense in term of retesting cost and some anesthesia. Means you find out based on the data that okay, one particular guy is having cancer which he was not having. So it's okay, it is a false positive, it's still okay, means he will have to go to the retest on those things, and obviously the retest cost and the the worry and other things which he will be having. So obviously false positive is also a cost, but just think of the case of the false negative, when this cancer was there but we put it that it is not there. So finding a cancer that does exist and we put it as it doesn't exist, it's really, it would be a cost of life. So that's why if you will see the finding of evaluating this classifiers, it's really two things you should measure with all the metrics like your confusion metrics and AUC and the percent correct and all, so that you can in the end you can say that yes, our model is perfectly defined and it's working as good as possible. So there are certain other things also, like one more strategy is there in the Mahout, which is called dissecting a model. So we will see an example also for that, dissecting a model. So first of all, what this dissecting a model means. Dissecting a model is like, we wanted to see in our model what are the features are making a large difference in the output. So nothing but if in the if I would like to rephrase this sentence, it is like we are having the predictors variables, we just wanted to find out which is really affecting more to the output or our target variable. So that particular thing we can find out using the dissecting a model strategy. And for this particular one, Mahout is having two classes. One is called abstract vector classifier and other is model dissector. So you will have to actually implement that, you will have to extend that abstract vector classifier, it's an abstract class, and then you will use the model dissector to create your own strategy to find out this particular model dissector. So if you will see here what I am saying, this abstract vector classifier, this is a class, this is abstract class, you should actually extend this. And then the second one is the model dissector, which can be used to find out this particular thing, that which feature is actually creating more weightage to the output. So feature we know that we will use as a predictor variables, as I already told you, and those variables we will first use the tokenized strategy and then vectorized that one, so that our algorithm can use in Mahout. So and these features, these vector features are actually clue which we will try to examine in this dissecting a model example. So this model dissector, it will take three inputs. One is your feature vector, which you after the tokenized and vectorized process you come up, and then it will take the trace of that how this feature vector is constructed, and your model it will take. So after tweaking this feature vector internally, this model side sector tweaking means some of the items it will try to remove, or some little weightage for one particular variable, and all these strategies it will apply, and then it will try to find out that how model output is changing. So if let's say you are having three features, and based on let's say you removed one feature, then you are looking at the output with the training set, and or you gave a different weight of a particular different feature in logistic regression, then you will try to find out what is the output, how output is affecting, and then it will do, whatever output it is coming, it will average over a number of examples using these strategies, this model dissector, and it will try to affect the different features. It will try to see how these different features are affecting. So this model dissector will provide, in the end, it will provide you a list of most important variables in your vector set or in your predictor variables which are affecting the output of the model. So the roughly code I would like to show you that how, if you are going to implement this, how it will be. this is the one that if you are going to implement, first you will have to close your model, means in your learning algorithm you will have to close, so that now new data is not coming into in this one. Then there will be a trace dictionary, as I told you. You need traces, you need a feature vector, and you need a model for the input. So in the trace dictionary also you will clear it out, and then you will use this model dissector. And here if you will see this for loop, means lots of example, means lots of features, different features you will use here, and then you will give it to the encoder feature vector, this example, and actual value of that, and this leak type. Leak type is nothing but your tweak type values, and then in the last it will give you the summary of the features which are having the weight on the calculated output. So it will tell you that okay, this feature is having this much of particular weight, and that particular weight is how it is affecting your model output. So you can see something in this definition in this model dissector class itself, if you will examine this API. So what, how this model dissector will be helpful? It will tell you whether this model is properly trained, and it will tell you that okay, most important variables are taking into consideration for the problem domain. And it will also tell you, if let's say your model is not perfectly working, it will tell you that okay, it is a broken model, and the most important variables which are supposed to taken as a predictor variables, or which are supposed to give in the more weightage, are not giving the weightage on the classifier. So this is about the model dissector in the performance metrics. It's a part of the performance metrics only. And then we will go back to this slides. So this confusion matrix we have already covered yesterday. Again, just for the repetition side, actual values are in the rows and predicted values in the columns, and then we will try to find out how many true positive, true negative, false positive, and false negative we are getting. Entropy matrix, as I told you, this is also a feature. If you will see in our example also, we were getting AUC, confusion matrix, and side by side we were getting the entropy matrix also. And entropy matrix is not different with the confusion matrix, but what it will do, it will take the logarithm also for those values which are coming in the column and rows. So if you will see this thing, the difference is that the element of the matrix are average of the log of the probability score for each true or estimated category combination. So it is just a matter of formation, how this matrix is formed. But I would say still, means in our scenarios and all, we are taking in Mahout side, we are taking more weightage for the confusion matrices. And then there is something, okay, for this entropy, like you saw in the confusion matrix, also we are having a classes. So same way for the entropy matrix also we are having the API supported into the system. So we can just read that matrix also as we were getting in the output. So we can get and we can find out what is the values are coming, and then we can try to manipulate also. If we not manipulate, we can get the actual values of those metrics in the programmatic way also, instead of in the command line you are providing that. Target leak. This is again an important thing in the classifier. So it's actually a bug. Like this, your target leak is a bug. Like in your simple Java program, you can compare this as a like your out of memory errors and those things. So this target leak is what it does. It is having the information of target variable included in the predictor variables used to train a classifier. So when you are making a model and you have selected some of the predictor variables, and so what you are doing in those variables, you are providing a feature so that your output is always matching with the target variables. So how you can do this means, if there are a possible things, first of all you should not do this, by mistake also it can happen. So let's say our 20 news data itself. So we saw that their data is having the 20 different articles. So if we wanted to get this target leak problem, what can happen? Let's say in those articles you are defining the date and month also, like you are defining a date timestamp. date, month and year. And what you did, you are putting that, okay, for a one particular month, all the articles will go into this particular category article. So in this way, it is directly you can know the output. So this date, if you are using as a predictor variables, so based on the date, based on the month, you can find out that, okay, in this month this article will go to this particular folder. So always your particular model will always give you 100% result, because you introduce something called a target loop there, something which is affecting your output. That information you have given to the system. So it will always give you 100%. And how means, if really your model is always giving 100% results and all, it's, I would say it's sometimes matter of concern also, that okay, how it is happening in the training and testing data. So this target leak could be a problem when you are directly defining that, okay, if in this particular month all the article will go to the, let's say, sports category from this particular journalist and all. So in that one, what you are doing, so in the predictor variables, you are defining the name and date also. So based on that, the system can easily identify that, okay, it will go into this one. But in the actual scenario, if date will not come, then your system obviously will not perform that. So that is called the target leak. And there is something other things, other one also a problem or bug, you will say, that is called a broken feature extraction. So broken feature extraction is like, you know, a broken feature extracted means which can actually create worse performance than expected. Means let's say your web tokenizing can lead to this problem, where you are using this using thing, and you are using your tokenizing strategy, or let's say you are using some third-party tool for the tokenizing thing, and you missed to tokenize your word properly. So you use some of the words which are, you know, occurring very frequently. If you remember our example, we dropped that two keyword from the set, because we know these are the frequent words, and it will not affect the our system. But if you will include that, then result can affect. So it is called a broken feature extraction as a bug into the system. So if you see this tuning the classifier, so if we want to change the data that's presented to the classifier learning algorithm, it is possible to change the algorithm or to modify the parameter that define the algorithm. So that is also a part of the tuning one that I was telling you. So you can change your problem statement also. So, and the benefit of trying these approaches is that it provides you with a variety of ways to improve performance through guided trial and errors. So, and one more thing, don't think, you know, whenever you are having a testing, you are having a data set, you divided it 80-20 rules, like 80% as a training and 20% as a test. And then you have created a model using training, and you tested with the 20% data, and it is really giving a wonderful results and all. So it is not like, you know, you can directly put it in the production and you are very happy that, okay, in the test data it was performing very well. You should actually try to find out the new data set, or change the data set percentage and all, and try to check model again and again to find out whether it is really good, or we did some mistake like target leak or those things, and that's why it is giving us the good results.